Imagine you've just migrated like 10,000 meticulously written articles into your brand new Next.js application.
Oh boy.
Right. You've spent weeks optimizing the front end. Your Lighthouse performance scores are perfect. The Edge network is just blazing fast, and the UI is completely flawless.
Sounds like a dream scenario so far.
It is until your editorial team makes a seemingly simple request. They say, they want to dynamically group all content-tagged electric vehicles along with lithium batteries and charging infrastructure into this unified auto-updating hub page.
And let me guess, panic sets in.
Total panic.
Yeah.
Suddenly, your front-end query logic devolves into 1,000 lines of completely unmaintainable spaghetti code. Your edge functions start timing out, build times skyrocket, and the entire system just practically grinds to a halt.
Yeah, you built the walls and the roof perfectly, but you completely forgot to install the plumbing.
Exactly.
That scenario is, well, it's the absolute definition of architectural technical debt in a headless ecosystem. Developers often treat content modeling as just building isolated containers. Title string here, a rich text body there. But creating those containers is really only 10% of the job.
Because if you fail to engineer a dedicated system to relate them to one another...
Right, precisely. If you don't engineer that centralized system, you are shifting the entire burden of data relationship management onto the front-end client. And that is computationally expensive, highly error-prone, and it just scales incredibly poorly. You need a centralized graph of relationships. You need a taxonomy.
And that is exactly why we're here today. Welcome back to The Deep Dive. We're speaking directly to you, the developers, the enterprise architects, and the systems engineers who are tasked with ensuring your content infrastructure doesn't just collapse under its own weight.
Absolutely.
This is Taxonomy Foundations Part 2. And our mission today is highly technical and extremely specific. We are moving entirely past the theoretical discussions of, what a classification system is. We are opening up the terminal today.
The theory is established. Today is strictly about execution and infrastructure.
Yeah.
Our goal is to give you a comprehensive step-by-step technical roadmap for mastering the life cycle of taxonomies right within the Contentstack ecosystem.
So we're covering everything.
Everything. We'll cover the mechanics of importing and exporting complex structural data, securely configuring your API testing environments, manipulating the content management APIs to build hierarchies programmatically, modifying content type schemas, and finally, executing highly optimized front-end delivery queries.
So if we're going to lay that structural plumbing properly, I feel like the first major engineering challenge is almost always data migration.
Oh, without a doubt.
Because very few enterprise applications start from a completely blank slate. You are almost always bringing in an existing classification system from a legacy CMS. Or maybe you're bootstrapping a new staging environment that needs to perfectly mirror production.
Right.
Getting a massive, complex taxonomy into Contentstack programmatically is really step one.
And the mechanism for that import, it relies entirely on JSON. Within Contentstack, every single piece of structural metadata, and that includes taxonomies, is inherently stored and transported as JSON.
JavaScript object notation.
Exactly. And this isn't just some convenient formatting choice. It's the absolute bedrock of how the headless database operates.
Because JSON is naturally nested, right?
Exactly. Because it's naturally nested, it allows you to take massive, multi-layered hierarchical graphs from external systems and map them directly to the Contentstack schema. And you do this without any tedious manual data entry.
Okay, let's unpack this a bit, because looking at the structure of a standard taxonomy, it is effectively a directed acyclic graph, or a DAG.
Right.
You have a root node, which branches into child nodes, which branch into leaf nodes. It's essentially like moving houses.
Like that analogy.
Yeah, instead of packing 100 physical boxes one by one, you just hand the movers a digital blueprint, which is the JSON file, and the house instantly rebuilds itself in the new location.
That graph materialization is the key concept here. When you feed that JSON file into the system, the parser is doing a tremendous amount of heavy lifting for you.
Like validation.
Yes, it validates the schema. It ensures there are no circular dependencies because obviously a child node cannot be its own grandparent. And it sequentially builds the internal relational pointers.
That is massive for CI/CD.
It's how you achieve absolute parity. You maintain your global taxonomy JSON file in a Git repository. When you spin up a new ephemeral testing stack, Your deployment pipeline just hits the import endpoint with that JSON payload.
And boom, the taxonomy is reconstructed identically in milliseconds.
Exactly.
Which totally eliminates the human error vector. I mean, if a front-end React component is strictly expecting a category tag with the exact UID of, let's say, advanced robotics,
Right.
if someone does manual data entry and staging and accidentally types advanced robotics singular, that breaks the query, the build fails.
And someone loses a weekend debugging it.
Exactly. The JSON import guarantees that the UID strings are exact, environment after environment. But, and this is a big play, but data mobility in a robust pipeline requires bidirectional flow.
It goes both ways.
Right. Moving data into a headless system is only half the battle. If we treat this schema as code, we need a way to pull the current state of the database back out into our repositories.
Which brings us to the export functionality. Extracting a taxonomy out of Contentstack is just as critical for things like auditing and version control.
So how does a developer actually do that?
Well, there is a UI method for this. You just navigate to the settings panel. You can actually just hit the S shortcut key, select taxonomy, pick the one you want, click the ellipsis in the actions column, and hit export.
And it just downloads locally.
Yes, but the true architectural value here lies in understanding the output formats provided. The system offers two distinct export payloads, JSON and CSV.
Now, the JSON export makes immediate sense to me based on what we just discussed. If I export as JSON, I'm getting that exact directed acyclic graph blueprint back. I can save it as taxonomy-state-v2.json, commit it to my repo, and I have a perfect snapshot.
Exactly.
But the CSV option is fascinating to me. A comma-separated values file is, by definition, two-dimensional. It's flat. How does the system take a deeply nested, multi-tiered graph of parent and child relationships and accurately flatten it into a spreadsheet without losing the structural integrity?
That's a great question. It achieves that through a structural paradigm known as an adjacency list, or path enumeration, depending on the exact schema generation.
Okay, what does that actually look like in the file?
When the system flattens the graph into a CSV, it uses very specific columns to define the relational vectors. You'll typically see a column for the term's unique identifier, its localized name, and this is the crucial part, a column explicitly declaring its parent to it.
Oh, I see. So each row is a discrete node, and that parent to it column acts as the mathematical pointer to reconstruct the tree later.
Exactly. Even though the data is sitting flat in rows, the mapping instructions to rebuild the 3D tree are preserved in the columns.
Wait, if I'm a developer building an automated pipeline, am I really going to click through a UI and download a CSV?
Well, no. As a developer, you're strictly operating on the JSON payload for your Next.js data fetching and your Git commits.
Right.
But think about the SEO team, or the marketing directors, or the data scientists who are managing the global content strategy. They don't want to parse nested JSON brackets.
Oh, true. They want to open a CSV in Excel or Pandas, run VLOOKUPs, filter by level, and audit the terminology.
Exactly. Providing both formats ensures that the taxonomy serves its dual purpose. It's a strict technical schema for the developers and a strategic business classification system for the operations team.
But to orchestrate all of this, the imports, the exports, the schema modifications, we really can't rely on clicking around a user interface.
No, the UI is great for one-offs, but real automation requires APIs.
Exactly. If we are treating the system as infrastructure, we need a deterministic, programmable testing environment, which means we have to lock down our API testing strategy before we write a single fetch request in our application code.
And the industry standard tool for this, the one we'll focus on today, is Postman.
Right. But diving straight into Postman with a headless CMS requires a very strict configuration setup. You don't just paste a URL and hit send.
Definitely not. First, you have to download the official Contentstack Postman collections. These contain the pre-built REST templates. And crucially, you must configure your environment variables.
The environment variables are essentially the security boundary of your testing suite, right?
Exactly. Hard-coding authorization tokens directly into API request URLs is a severe security vulnerability. Plus, it makes switching between development, staging, and production environments incredibly tedious.
Yeah, nobody wants to manually swap keys every time they change environments.
Right. By utilizing Postman environments, you abstract the credentials. But the most critical architectural concept developers must grasp here is the bifurcated authentication model.
The two different tokens.
Yes, you are required to generate and manage two entirely distinct types of cryptographic keys, a management token and a delivery token.
I want to pause here because this is huge. Looking at the security context of a headless architecture, this split is non-negotiable.
It really is.
I mean, why the separation? Why do I need a management token and a delivery token? Why not just one master key for the stack? I've seen developers try to simplify their .env files by using a single master key for everything, and it usually results in a catastrophic data breach or massive rate-limiting failures.
It comes down to the fundamental difference between mutating state and querying state. Let's analyze the management token first.
Okay.
This token authenticates against the Content Management API, or the CMA. The CMA is a highly privileged read and write interface. It interacts directly with the core authoritative databases of your Contentstack environment.
It's powerful.
Extremely. When you pass a management token in an authorization header, you are given the power to create new schemas, delete taxonomies, overwrite data, and fundamentally alter the architecture of the space.
It is the equivalent of root database access.
Exactly.
If I'm building an Next.js application and I accidentally expose my management token in a client-side bundle that gets shipped to the user's browser,
Then any malicious actor who opens Chrome DevTools now has the keys to delete your entire production database via a simple CURL request.
it is a massive liability.
And beyond just security, the CMA is simply not engineered for front-end scale. Because it's executing complex database write operations and strict validation checks, it is subject to tight rate limits.
So if you tried to route 10,000 concurrent front-end users through the CMA just to read an article,
Your request would be throttled and blocked almost immediately. The database would lock up attempting to serve synchronous reads while maintaining write availability.
and that is exactly where the delivery token and the Content Delivery API, the CDA, step in to solve the scale problem.
Precisely. The delivery token is strictly read-only. It cannot mutate data. It cannot delete a taxonomy.
It's purely for fetching.
Right. And more importantly, the Content Delivery API does not query the core database directly for every request. It operates on a massive, globally distributed edge caching layer, a CDN.
Oh, wow.
So when you query the CDA with your delivery token, you are retrieving precompiled published JSON payloads from a server located geographically closest to the user. It is engineered to handle millions of requests with millisecond latency.
Okay, so the architecture rule is absolute. The management token stays securely locked in your backend CI/CD pipelines, your node scripts, or your Postman environment for building the house.
Yes.
And the delivery token is what you pass to your front-end application to allow users to walk through the house.
That's a perfect way to put it.
So once we have those tools installed and those tokens properly scoped and securely loaded into our Postman environment variable, say management token and delivery token, it's time to put the key in the ignition.
Testing the actual endpoints becomes incredibly fluid at this point.
What does that workflow look like?
Well, the workflow within Postman acts as a controlled testing sandbox. When you select an endpoint from the imported collection, Postman dynamically injects those environment variables into the request headers.
Ah, so you aren't manually typing them.
Right. For instance, testing a CDA query, Postman will automatically set the access token header with your delivery token and the environment parameter to whatever you've defined, like development or production. You also set the content type with maybe to blog post and fire a get all entries request.
And you just see a live JSON response right there.
Exactly.
Here's where it gets really interesting, Vinay. I always refer to this Postman setup as a wind tunnel for your application data.
A wind tunnel.
Yeah. Before you try to build the actual airplane, your complex Next.js front-end component, you use Postman to test the aerodynamics of your payload.
I see what you mean.
If I execute a GET request for all articles tagged with a specific taxonomy, I can inspect the raw JSON response right there in the terminal. I can check the time to first byte. I can look at the caching headers.
Right. You get full visibility.
And if the JSON structure is deeply nested and missing the exact fields I need, I know I have a backend schema problem. I haven't wasted hours debugging React state management only to realize the data was never there in the first place.
That isolation of variables is why API testing is mandatory. If the wind tunnel proves the payload is perfect, any subsequent issues are strictly front-end rendering problems.
Exactly.
So now that we've established the secure testing workflow, we must transition into the actual mutation of the system. We need to leave the read-only edge network behind, access our management token, and interface directly with the content management APIs to build a taxonomy from scratch.
Putting on our backend engineering hats now. Looking at the CMA documentation, it outlines several core REST operations for handling taxonomies. You've got get all taxonomies, get a single taxonomy, get a single term, and most importantly, create a term.
Right. And while the GET requests are standard data retrieval, The post request to create a term is where the structural complexity of that DAG, the directed acyclic graph, truly reveals itself.
Because we are dealing with a strict hierarchy. You aren't just throwing a string into an array. You are placing a very specific node onto a very specific branch.
The precision of that placement is dictated entirely by the JSON payload you send in the post request. Let's analyze the construction of a parent-child relationship via the API.
Okay, let's do a real-world example.
Suppose you are building a global e-commerce taxonomy, and you need to establish a root category called electronics. A root category, by definition, has no superior node. It sits at the absolute top level of the tree hierarchy.
So looking at the payload requirements, to create that root node, the developer must explicitly pass a parameter called parentuid, and the value assigned to it must be null, right?
Yeah.
Hold on, if I explicitly tell the API that the parent is null, doesn't that usually mean an error or missing data? In a lot of programming languages and REST paradigms, sending a null value implies you forgot something, or it tells the database to clear an existing field. It frequently triggers validation errors.
That's true in many systems, but here, null is an active command. It is a deliberate, explicit architectural declaration.
Okay, how so?
In the context of this specific schema, parentuid, null does not mean I forgot to include the parent. It translates to a database instruction. This term answers to no one. Initialize this node with 0 incoming relational edges. Designate this as a root vertex.
Oh, wow.
The system requires this explicit null declaration, along with defining the level as 1 or above, to validate the integrity of the top-level structure.
And then the logic shifts immediately when you want to build downward. If I have successfully created the electronics root node, the system auto-generates a unique identifier for it. Let's say it's term electronics 0. If I now want to create a child term called laptops, I construct a new post payload. But instead of sending null, I pass parentuid, term electronics 01.
Yes, you are explicitly passing the pointer. The API validates that the parent UID exists, locks the relational edge, and creates the child node.
You're programmatically building the tree branch by branch, edge by edge, through sequential post requests.
But keep in mind, this entire process operates on the assumption that the overarching taxonomy container, the master graph object itself, already exists to hold these terms.
All right.
If you're automating a massive deployment, manipulating the terms is actually the second step. The very first programmatic action is creating the new taxonomy container itself via the CMA.
Which means bypassing the manual UI steps entirely. Instead of clicking new taxonomy, typing a name, and saving, we replace all of that with a single automated REST call.
Yes, a post request to the base taxonomy's endpoint.
And the required payload for that is remarkably minimal, right? It's essentially just a JSON object containing a name and a global 8. Something like name, global e-commerce, 8 global commerce.
Exactly. You authenticate with a management token, fire the request, and the container is instantly initialized in the database.
This feels like the ultimate shortcut.
Oh, it's vital. The strategic value of this automated creation becomes apparent at enterprise scale. Consider a massive agency managing a multi-tenant architecture. They're spinning up identical localized stacks for 10 different international brands.
Brand 1, brand 2, brand 3.
Right, and they all must share the exact same underlying global classification structure. If you rely on a human operator to log into 10 different regional environments and manually click together a taxonomy with 500 terms,
the failure rate approaches 100%. Someone is going to misspell a UID. Someone will accidentally nest a term under the wrong parent.
And months later, when the global data pipeline tries to aggregate sales for the laptop's UID, the query fails because in brand 3 stack, it was accidentally typed as laptop singular.
Automation via the CMA eliminates that drift completely. You script it once. That script authenticates against the 10 different environments sequentially. It posts the taxonomy container, then iterates through a source JSON file, firing the POS request to create the root terms with null parents, and then recursively p-posts the child terms with their explicit parentuid pointers.
In 60 seconds, you have guaranteed mathematical parity across 10 disparate databases.
You engineer the graph once and you deploy it infinitely.
Exactly. But executing that creation request isn't the end of the back-end journey. You can't just assume it worked perfectly. The network is inherently unreliable. Databases experience lock contentions.
Right.
If you write an asynchronous bulk creation script, you have to verify the state of the database, which introduces the necessity of using the content management API to actively read the taxonomy information back.
Okay, so fetching and reading existing taxonomy data via the CMA.
Yes, hitting the endpoint to get detailed information about a single taxonomy.
But wait, if I just created it, why am I immediately reading it? What's the value here for the developer? If I wrote the deployment script, I already know the names of the terms I pushed.
You know the names, but because of the principle of eventual consistency in server-side mutations, you don't have the full picture. When you create elements, the Contentstack system performs internal operations. If your script didn't explicitly force a specific UID for every single term, the database automatically generates hashed unique identifiers for them.
Ah, I see.
You do not know what those auto-generated UIDs are until you read them back.
And without those UIDs, you are basically flying blind. Those specific strings are the technical glue of the entire system. Because if I want my front-end Next.js application to query for laptops, it doesn't search for the English word laptops. It searches for the exact UID that the database assigned.
Furthermore, reading the data back from Postman allows you to inspect the JSON response and validate the structural graph. Did your asynchronous script encounter a raised condition where a child term was posted before its parent finished creating?
Oh, that's a great point.
Did the API return a 422 unprocessable entity error that your script swallowed? Fetching the taxonomy payload allows you to verify that the hierarchy of terms is structured exactly as intended.
It's exactly like using state files in Paraform. You declare what you want, you apply it, and then you read the actual state to ensure it matches.
Precisely.
Okay, but speaking of binding things together, a pristine taxonomy floating in the void of the backend database doesn't actually do anything. It's an isolated graph. We must attach it to our content models.
Yes, we are now shifting focus from back-end management to content modeling. To actually use a taxonomy, developers must manipulate the schema to inject a specialized taxonomy field into an existing content type.
And analyzing the documentation for this, there's a very strict platform constraint. Contentstack enforces a rule. Currently, you are permitted to add only one single taxonomy field component per content type.
For developers accustomed to sprawling database tables with 50 different relational foreign key columns, that constraint can initially feel highly restrictive.
I can imagine.
If you have an article content type, you might logically assume you need one field for topic taxonomy, a second field for region taxonomy, and a third for author taxonomy.
But restricting it to a single component forces a much cleaner paradigm. So what does this all mean? Imagine your content type is a filing cabinet. You only get one master index drawer that's the single taxonomy field. But inside that drawer, you can pull index cards from multiple different libraries, like a superhero library and a genre library.
That's exactly how it works. Within that single field, developers can select one or more taxonomies to use. It establishes a unified entry point for all metadata relations, preventing the schema from becoming bloated.
Theory is great, but let's walk through exactly how you configure that filing cabinet in the system. Let's do a step-by-step practical walkthrough of applying that taxonomy to the content type in the UI.
Okay, the listener can follow along here.
Yeah.
First, you navigate to the content models window in the UI.
Got it.
Then, you edit an existing content type. Let's say we have a character content type.
Okay, opening the character content type.
You look at your available fields, and you drag and drop a new taxonomy field into the schema.
Right.
Once it's in the schema, you open its properties. There, you'll see a configuration option allowing you to select the desired taxonomy. You select the superhero taxonomy we built earlier.
And then you just save the content type.
You save it, and the moment that's done, the internal architecture shifts. The content editors finally see the fruits of the developer's labor.
Because now, when an editor logs in and creates a new entry for, say, Dr. Strange, they are presented with a dynamic taxonomy interface.
Right. They aren't just typing unstructured tags into a generic string array, hoping they spell mystic origins correctly. They can now tag character entries with predefined terms like mystic origins or super strength.
The interface forces the editor to select an explicit node from the tree. And the resulting JSON payload for that Dr. Strange entry now contains a locked relational pointer mapping directly back to the global taxonomy graph.
The data is structured, validated, and mathematically clean.
Which means the back-end engineering is officially complete. We've built the graph, modeled the content, and the editors are tagging. Now, how does the front-end developer retrieve this beautifully categorized content for the user? We switch entirely to content delivery.
Yes. The delivery side relies on highly specialized query operators provided by the Content Delivery API, the CDA, or the JavaScript SDK. And the most computationally powerful tool at your disposal here is the equals or below taxonomy operator.
Let's dissect the logic of the equals or below query, because this operator leverages the hierarchical nature of taxonomies, right?
Exactly. If we look at a standard media site, suppose we have a taxonomy for the animal kingdom. We have a root term mammals. Below that, child terms for dogs and cats.
Okay, the hierarchy is set. Now a user navigates to your Next.js site and clicks the main navigation link for mammals.
Right. If a developer constructs a standard, rigid query asking the API to return entries where the taxonomy strictly equals mammals, they will encounter a massive data retrieval failure.
Wait, why is that a failure?
Because an editor writing a highly specific article about a golden retriever is going to tag it exclusively with the dog's leaf node. They're not going to redundantly tag it with mammals. A strict equals query for mammals looks at the dog article, sees a mismatch, and filters it out.
Oh, so the high-level category page ends up completely empty.
Exactly. This is where equals or below comes in. When you query for terms equals or below the parent term mammals, the API doesn't just return entries tagged exactly mammals, it performs a recursive descent.
Oh, so it intelligently returns all entries tagged with child terms like dogs or cats as well.
Yes. It traverses every single outbound edge. It aggregates the matches for mammals plus dogs plus cats, compiles them into a single payload, and returns it.
Wait, isn't that going to pull in too much data? What if I just wanted a list of general mammals, not every specific dog breed? This feels computationally heavy.
That is a very valid pushback.
Yeah.
And it's a vital architectural consideration. Graph traversal is heavy. If you execute an equals or below query on a massively broad root term, you could aggregate 50,000 articles and crash your build.
Right.
The equals or below operator is perfect for generating dynamic breadcrumbs or broad category pages, but it requires the taxonomy tree to be logically sound. And you must implement strict pagination and limit parameters in your query to protect the front-end memory.
Okay, but what if I don't want the whole family tree at all? What if we are building a specialized UI component, like a highly curated featured products carousel on an e-commerce homepage? We want a very specific hand-picked selection of terms, ignoring the broader hierarchy completely.
That brings us to our final technical capability. We conclude the deep dive by explaining querying using the taxonomy in operator.
The again operator.
Yes. If equals or below is a recursive traversal, the in operator is a strict set theory intersection. This CVA query method is used to fetch specific categorized entries by matching them against a discrete list of terms, completely ignoring the broader hierarchy.
So we are trading the broad dragnet for absolute precision.
Exactly. Let's look at a multi-brand e-commerce site. You have brand 1 and brand 2 in the same database. The data isolation requirements are absolute.
Right, you can't have brand 2's discount products bleeding over into brand 1's luxury page.
Exactly. So a developer might use the IN operator to fetch products specifically tagged EN in an array like brand 1 shoes, brand 1 accessories.
Ah.
The API scans the database and only returns an entry if its taxonomy metadata contains an exact intersection with the terms in that discrete array. It ensures no content bleeds over from other categories.
So equals or below is for casting a wide hierarchical net, while in is like using a spear to pick out exact tags. That gives front-end developers total control.
It does. And that final step completes the entire journey. From importing raw JSON to building the hierarchy via the CMA, attaching it to a content model, and finally pulling it seamlessly into a Next.js frontend using these precise operators.
Synthesizing all of this, the technical arc we just traversed is staggering. I mean, congratulations to everyone listening who mapped out the full technical life cycle of a taxonomy and Contentstack with us today.
It's a massive shift from building static data containers to engineering a dynamic relational ecosystem.
It really is. But before we sign off, we want to leave you with a deeper architectural thought to mull over something that builds on this infrastructure.
Right. Consider the principle of decoupling. By decoupling your category logic, your taxonomy, from your actual data structures, your content types, you aren't just organizing a website today. You're actively future-proofing your content for channels, apps, and devices that haven't even been invented yet. Think about how your current rigid content models could be set free by abstracting their metadata into a global taxonomy. Because the relational metadata exists independently, your data is inherently fluid and ready to be routed exactly where the architecture demands.
That is incredibly powerful. Don't just build the containers, architect the systems that connect them. I invite you to open Postman, grab your tokens, and start experimenting with these APIs firsthand. Because once you master this blueprint, you can scale anything. Keep testing, keep building, and until next time, keep diving deep.